Hi, welcome to PEC Explains Physics. Today we are going to start a new chapter called Mechanical and Sound Waves. So in previous chapter, Simple Harmonic Motion, which is our chapter 9, we have learned about oscillation of spring mass system. Spring mass, okay, the block is actually considered as only one particle. Okay, so in Simple Harmonic Motion, chapter 9, we just learned the oscillation of the block, the one particle, oscillation of this block over time. Okay, it's just the oscillation of only one particle, oscillation of the block up and down over time. So we use this equation x equal to a sine omega t to describe the oscillation of the block. At different time, the block has different displacement. Okay, so oscillation, this equation just shows the oscillation of one particle over time. And this is the graph, displacement time graph. So at different time, the block has different displacement. This graph, we can get the amplitude, we can get the period, okay? And be careful with the unit. You see, if this displacement is cm, the amplitude also cm. If the time is millisecond, the period also be millisecond. So be careful with the unit. So in chapter 10, okay, our chapter now, the mechanical wave. We are going to learn about mechanical wave. For example, like we have water wave, we have sound wave. All these are mechanical wave. They are called mechanical wave because they require medium. Okay, mechanical wave requires the medium to propagate their energy. Like water wave, it requires water medium. Sound wave requires air particle medium to propagate their energy. So we are talking about, in chapter 10, we are talking about the oscillation of the many particles in the medium in order to transfer the energy, to transfer the wave. Not just the oscillation of one particle like the block. This time we are talking about the oscillation of the many particles of the medium that transfer the energy. We can consider this like the water surface. Water surface has many water particles. All of them oscillate up and down in order to transfer the wave to the right. Okay, so we use this equation we use y equal to a sine omega t plus minus kx to represent the oscillation of many particles over time. Look at this. Simulation. You see, okay, I played. Now I played. Do you see that? This wave moved to the right. The wave moved to the right. But you see the particle? We have two particles here, oscillate up and down. Actually, not just two particles. The whole wave, all along the wave, it has many particles, all oscillate up and down. You see that? I put here. All of them oscillating. Many particles oscillating up and down over time. Alright. Now, let's look at this one. Yeah? Okay. So, we are talking about the oscillation of many particles of the water medium. Yeah? All particles oscillate up and down over time. So this time we modify the equation. Still almost the same type of equation, but we just modify. The x, last time we used x to represent displacement. Now we change the x to y. Same meaning. The y still means displacement. Same meaning. Why we need to change to y? Because now we use x to show which particle. It is actually the position. X is the position from the first particle. Like you see this water wave. Let's say I want to take this particle. Okay, this particle is x distance from the source. This particle is x distance or x meter from the first particle. So x is not showing the displacement already. X is the distance from the first particle. Or we can say x is also the position of the particle in concern. Okay. Now we use y to represent the displacement of each particle. See this one, the y. And the y is the displacement of each particle. So what does it mean by this equation? This equation means which particle at what time and it has what displacement. Okay, this equation means the displacement of certain particle at certain time. Okay, so this time we use two graphs. In this chapter, we're going to learn two graphs. The first one, of course, is displacement time graph. The second one is displacement distance graph. What's the difference? Okay, let's hear me. Displacement distance graph shows the whole wave of many particles. The whole wave. You can see the whole wave at certain time. So this displacement distance graph, you can see the whole wave at certain time. So since you can see the whole wave, that's why you can get the wavelength for the x-axis. You can get the wavelength lambda. Okay, you can see many particles at different displacement. Okay, the whole wave at certain time. The displacement time graph, it shows the oscillation of only one particle for certain position. Maybe I'm taking x equal to 3 meter. That means maybe over here, this particle, maybe I'm referring to this particle over here, which is x equal to 3 meter away. This one, okay? This particle, this y displacement versus time graph means the oscillation of x versus x equal to 3 meter particle up and down over time. This graph shows the oscillation of this particle up and down over time. So that's why this graph can give us the period. Because it shows us how much time it used to complete one oscillation. The time to complete one oscillation is one period. Okay? So this is the displacement versus distance graph is you can see the whole wave profile at certain time, but displacement time graph, it shows the oscillation of one particle at certain position over time. Okay, so displacement distance graph gives us the lambda, because you can see the whole wave, you can get the wavelength. Displacement time graph, you can get the period because it shows the time taken for one particle to complete one oscillation. You can get period. Okay, so this is very important. Both graph you can get amplitude. Both graph can get amplitude, but the displacement distance graph can get lambda. Displacement time graph can get period. This lambda and period very important. Period you can change the frequency because f equal to 1 over period. So you can get the frequency. So from frequency multiply lambda, you get the wave speed. You use the lambda here, you use the frequency from period, f multiply lambda, you can get the wave speed. That means you can get how fast the wave propagate to the right or to the left, which is this one. You see? Let's play. You can get how fast the wave move to the right. Yeah, the whole wave move to the right. That is wave speed. V equal to f lambda. Okay. Now that's about the what. Okay. Okay, and be careful with the unit. This amplitude, you need to check the unit. Y is meter. This amplitude also meter. Yeah, amplitude is meter. This lambda is must check the x-axis. It is in meter, so lambda is meter. Sometimes can be in cm. If x is cm, the lambda is cm. If the y is cm, the amplitude is cm. Okay, and the period you need to check the time axis. If the time axis the unit is millisecond, then your period is millisecond. So be careful. Next, yeah. Now I want to go into detail about this equation. As I mentioned just now, the y is showing the displacement, yeah, but the x is showing the position of which particle. Okay. Still, the in front here, A is showing the maximum displacement, or called the amplitude. Okay, amplitude. Yeah, the positive negative here, it means the wave direction. If this is a positive value, positive kx, okay, positive value means the wave moves to the left. If negative value means the wave moves to the right. Yeah, this means this one. Like this one. This wave move to the right, isn't it? This wave move to the right. This wave move to the right means this is a negative kx. Negative. If the wave move to the left, then it's positive kx. Okay? Alright. Now let's look back here. Yeah, so this positive negative means the wave direction. Okay. Now the omega. This omega is omega t. In front of the t, you can get omega. This omega is called angular frequency. Angular frequency. Angular and omega is 2 pi over period, or 2 pi f. So period is second. So omega is per second. That's a unit for omega, per second. And then we have kx. In front of the x is k. K is called the wave number. Wave number. So k is equal to 2 pi over lambda. Yeah, wave number is 2 pi over lambda. Lambda is meter, so k is per meter. So similarly, if lambda is cm, then k is per cm. So you must check the unit always. Yeah. Yeah. Okay. So you see, from omega, omega is referred to the period. K is referred to the lambda. So for omega, you can get period or frequency, but K can get lambda. So these two is important. We can get frequency from omega. We can get lambda from K. So after you have frequency and lambda, we multiply together F lambda, we can get the wave speed. Alright? So from omega here, you can get frequency. Omega get frequency. From K, you get lambda. So F, the frequency from omega, the lambda from K, you can multiply F and lambda, you can get the wave speed. Okay? Now, the next thing is particle vibrational velocity. What's the difference? Now we have another type of velocity called particle vibrational velocity. What's the difference between particle vibrational velocity with the wave speed? As I mentioned just now, wave speed V equal to F lambda. What is V equal to F lambda? Wave speed means the speed of the wave, the whole wave profile moving to the right. See this one, the whole wave moving to the right at constant speed. Yeah, wave speed is always constant. Always constant. Okay? Wave speed is always constant. V equal to F lambda is always constant. But particle vibrational velocity is the velocity of the particle oscillating up and down, which is this one. You see here there are two particles. So this particle, it oscillates up and down, and the speed is not constant. The speed is 0. The velocity is 0 at amplitude, maximum at equilibrium, 0. You see, velocity 0, velocity maximum at equilibrium, velocity 0 at amplitude, velocity maximum at equilibrium, 0 again. So this is called particle vibrational velocity. And different particle has different vibration velocity, you see? A different particle at different time has different velocity. So this is called particle vibrational velocity. That means the vibrational velocity of the particle oscillating up and down. Yeah, we have so many particles. All particles has different vibrational velocity at different time. So How to find? How to find the vibrational velocity of each particle oscillating up and down? So same like before, it's just the same like before. In simple harmonic motion, we also try to find, we have a displacement time graph, a time equation. We can find displacement. We also find the velocity of the particle. We also find the velocity of the block oscillating up and down. Right or not? We got the displacement of the block. We also got the velocity of the block. We also got the acceleration from the block. How we find the velocity of the block? We differentiate the displacement time equation. V equal to dx over dt. Differentiate, we get velocity. And then differentiate the velocity again, we get acceleration. So the same thing we will do for this equation. To get the velocity of the particle oscillating up and down, we differentiate the displacement time equation. Differentiate the displacement equation against time. A sine omega t plus minus kx, we differentiate. Differentiate the sign, we get cos. And then differentiate inside, we differentiate omega t, we get omega. Omega go to the front. That's why the velocity equation is A omega cos omega t plus minus kx. Okay? So same thing. The maximum velocity is still A omega like before. Yeah. Maximum displacement is A. Maximum velocity is A omega. Maximum acceleration is A omega square. Just like before in chapter 9, simple harmonic motion. And when we have maximum velocity, A omega, it is at the equilibrium. That means when this particle go to the equilibrium, it has maximum velocity. Yeah, over here, maximum velocity A omega. At the amplitude, velocity is 0. Okay? And particle vibrational velocity is changing. Like waves, like just now I said already. Yeah? You see the wave speed. The wave speed is constant going to the right, isn't it? Wave speed is constant. But particle vibrational velocity always increase, decrease. You see the arrow? You see the arrow? It become longer, become shorter. Means the arrow represent the velocity. Arrow represent the velocity. So you see the velocity going faster, 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 faster. Slower, slower, slower. Stop. You see stop, change direction. Velocity go down. Velocity go down, increase, decrease. Velocity become 0 again. So the velocity always changing. You see the arrow changing? The arrow changing means velocity changing. So particle vibration velocity always change over time. Okay? Particle vibration velocity. Particle vibration velocity is changing with time. Also, different particle at different time has different velocity. Okay? Now, we also can use the displacement. You see, the earliest equation is displacement time equation. We already have the displacement time equation. Now we got the velocity time equation. Velocity versus time. If the question gives you displacement to us to find the particle vibrational velocity, okay, give you the displacement and then you need to find the velocity. We use the velocity displacement equation. This is the same as chapter 9, simple harmonic motion. We used this equation before, V equal to plus minus omega square root A square minus X square. So remember we use X square. Now we don't use X, we use Y. Because why? Because X we used to show which particle. Now the one carry the same meaning as displacement is the Y. So we use Y already. So in this chapter we use Y because this Y is because this is displacement. So Y, we use Y as displacement now. Yeah, in chapter 10 we use Y. In chapter 9, simple harmonic motion, we use X. So chapter 10 we use Y as displacement. So this is velocity versus displacement equation. Same function like chapter before. Okay. Now, for particle acceleration, we just differentiate the velocity equation to get the acceleration. Then we can get the acceleration versus time equation. Differentiate the cos, we get negative sign. Differentiate the omega t, we get another omega. Go to the front, become a omega square. Right? So this is the equation, a versus t equation. And the maximum acceleration is still a omega square. And maximum acceleration happens at the amplitude. When you have a maximum displacement at the amplitude, the particle has the maximum acceleration towards the equilibrium. Okay, a omega square. And we also can use the acceleration versus displacement equation. A equal to negative omega square y. Last time is a equal to negative omega square x. This time our displacement use y symbol, so that's why we change to y. A equal to negative omega square y. Okay, so we have the acceleration versus displacement equation. So that's all for this, the first part. So I just want to let you know that the difference between the wave speed and particle vibrational speed. Wave speed is the speed of the whole wave. Particle vibrational velocity is the velocity of each oscillating particle in the medium. Okay. And then yeah. So in chapter 9, we just concerned about oscillation of one particle. This time we consider the oscillation of many particles over time. That's why we have extra kx here. X is to represent which particle you refer to. Yeah, which particle at what time have what displacement. That's what it means. Okay, and we have two graphs. We have displacement distance graph. We have displacement time graph. Displacement distance graph, it shows the whole wave. You can get the wavelength of the whole wave. You can see the whole wave frozen at certain time. Yeah, the whole wave frozen at certain time. That's why you can measure the wavelength of the wave. And y versus t graph shows the oscillation of just one particle with time. Yeah, up and down with time. So you can know the period which is the time taken for the one particle to complete one oscillation. Period is the time for the particle to complete one oscillation up and down. Okay, so y versus x shows the whole wave at certain time. Y versus t shows the oscillation of one particle at certain position. Okay, so that's it for the first part. I hope I didn't miss anything. Okay, I hope you got everything written down. Yeah, please make sure you write down the notes. Yeah, so now let us continue to the second part. See you. Bye.